The signal from the Lagrange Point personal log of the RAS-24 Oriole radio telescope operator. Time 0213. Weather overcast, wind about 7 meters per second. When the concrete under the dome cools at night, the lab takes on a different sound. The fans hum steadily. The hard drives whisper together. They resemble the breathing of a machine listening to the sky. I began the night observation window. Our frequency band runs from 1.2 to 1.8 gigahertz, the same radio range used by satellites and where astronomers often listen for cosmic signals. While the rest of the world sleeps, I start the automatic analysis, filtering out terrestrial noise, flattening and cleaning the data stream to catch anything that doesn't belong to Earth. On one monitor, the waterfall display shows live data frequency on the vertical axis, time on the horizontal, brightness for signal strength. Any strange, narrow line there might mean something unusual. An unexpected trace. At first, I thought it was interference, a thin, steady streak near 1420 megahertz. That's the famous hydrogen line natural radio emission from interstellar gas, and activity around it isn't rare. But this signal was too perfect, too clean, with an odd inner pattern, as if it were artificially generated. It looked like a PN sequence a pseudo-random signal engineers use for testing and calibration. It sounds like noise, but actually repeats in a strict pattern, easy to identify among random signals. I was about to mark it as a routine Earth-based interference when I noticed something. The signal was breathing. It strengthened and weakened slightly every couple of minutes, exactly what happens when a satellite's antenna drifts as it orbits. Checking the direction. To find where it came from, I contacted 2 other observatories in our network, BARS in Kazakhstan and Polaris near Tromsø, Norway. We recorded the signal simultaneously, then compared the time delays at which it reached each antenna. The differences let us estimate the source direction. The first calculations were strange. The signal seemed to come from somewhere between the Earth and the Moon, from the area where the gravity of both bodies balances out. That's the Lagrange Point L1, a place where satellites can hover, but not for long. The orbit is unstable, and without correction any spacecraft would drift away. I recalculated several times. The numbers stubbornly stayed around 320,000 kilometers. Too far for a normal satellite. Too close for deep space. The model error. To test the hypothesis, I switched to another model, one assuming the signal came from a nearby source, not as a flat wave from infinity, but as a spherical wave expanding outward. In radio terms, that's called the near field. After recalculation, the truth emerged. The source was much closer, roughly 36,000 kilometers away, right where geostationary satellites orbit. The earlier result had been a modeling illusion. The assumption of a distant source made the math draw a beautiful but false spot between Earth and Moon. In reality, the source was nearby, in the familiar belt of communications satellites. A familiar voice. But one question remained. Who, on the geostationary orbit, was sending out this old test code? I checked the public catalogs. In the right sector there was an old weather satellite, decommissioned years ago and moved to a graveyard orbit a bit higher than the active geostationary ring. Satellites at that altitude are usually asleep, but sometimes radiation wakes up their electronics, triggering old test programs. The signal had right-hand circular polarization, typical for older spacecraft. Its slow-frequency wobble suggested the satellite was slightly rocking or rotating. Everything fit. A link to the past. Then I remembered, 20 years ago, we had used a similar test code in ground experiments. It was entirely possible that this module had been built from those same templates. I called Liza, our radio systems engineer. "Looks like an old weather satellite stuck in self-test mode," I said. "Makes sense," she replied. "If its onboard computer got hit by radiation and rewrote part of its memory, it could get stuck in a diagnostic loop, repeating the same test pattern forever. It thinks it's still being checked, and it'll keep doing that until its power runs out." That line stayed with me. It's alive and thinks that life is a test. Confirmation. We collected several hours of data, corrected for atmospheric and magnetic effects, and re-ran the calculations. Everything lined up. The signal indeed came from that retired satellite. Its breathing came from the slow wobble of its body, and the old PN code was simply part of its test mode. The next morning, an official response arrived from the satellite's operator. Yes, it was their spacecraft, retired to a disposal orbit in 2011. Yes, spontaneous reactivations of the test module were known to occur during radiation storms. And yes, that very same code had been part of their system developed about 20 years ago. They promised to shut the beacon down. Echoes of our own signals. Later that day, I walked out to the antenna. The wind pressed against my face. The sky was gray. The metal dome of the telescope was cold as ice. All this time, I hadn't been catching a signal from deep space. It was an echo of our own era, a reminder that the sky is full of the footprints of human technology. We often say space is silent, but it isn't. It whispers to us in our own language through reflections, malfunctions, and old beacons. Sometimes it feels like a message from afar, from the balance point between gravities. But in truth, it's us, listening to our own past. Conclusion. The signal that first seemed like a voice from the Lagrange Point turned out to be an artifact, a modeling error, a retired satellite, and an old test code. No mystery, just physics, electronics, and memory, both human and machine. I turned off the recording. The even hum of the fans and the steady tick of the clock filled the room again like the heartbeat of the universe, calm, precise, and endless.